Hi, folks. We're starting a new section today on sequences and recursion. Let's get started. You've seen sequences in Calc 2, but let's look at them again. A sequence is just an ordered list. A1, A2, A3 up through, say, A sub k. The subscript is called the index variable, and it can reference any of the terms of the sequence. So when n equals 1, it references this term. When n equals 2, it references this term. When n equals 3, it references this term, and so on and so forth. Some books will begin with A0. Some will begin with A1. We're going to usually use A1, but sometimes we may specify otherwise. But I will let you know if we're not starting with A1. A sequence may be finite or infinite. I drew a finite sequence in the example, but it could go on forever. Okay? We say that an explicit A sub n has an explicit formula if it's possible to use that formula to compute whatever the nth term is directly. A lot of sequences will have an explicit formula, like the one in the next example. But some of them do not, and we'll look at some examples that do not also. So here's my formula. A sub n equals 5 minus n over 5 plus n. The instructions say to write the first three terms, so that will be A1 and A2 and A3. Well, A sub 1 will be 5 minus 1 over 5 plus 1. That's 4 over 6, which is 2/3. A2 is 5 minus 2 over 5 plus 2. And that's 3 over 7. And A3 is 5 minus 3 over 5 plus 3. And that's 2/8, which reduces to 1/4. If we wanted to compute A100, well, that's not bad. That's 5 minus 100 over 5 plus 100. And that's negative 95 over 105, or negative 19 out of 21. That is, because my formula has an n in it, I could just use that n, drop in the 100, and go straight out to this 100 term without having to compute everything in between. I can skip ahead using this formula here. We say that a sequence is recursive, has a recursive formula, if the formula requires referencing previously computed values of the sequence. And when that happens, we have to have some initial conditions to begin computation with. So here's a recursive formula. We're given these two values, C1 equals 1 and C2 equals 2. And the instructions say to compute C3 and C4 and C5. All right. So when we're computing C3 using this formula, K equals 3. And so it's equal to K minus 1 will be 2. Plus 2 times K minus 2 will be 1. And so C2 is 2 plus 2 times 1. And so this is going to be 4. All right, C4, K equals 4, is CK minus 1, so this will be C3 plus 2 times C4 minus 2 is 2. And so C3 is 4 plus 2 times 2 is 8. All right, C5 is C4 plus 2 times C3, and that's going to be 8 plus 2 times 4, and that's going to equal 16. Using this formula, it would be very slow to compute C100, because I would have to go through and figure out what C99 and C98 were. And then I'd have to go back and figure out what C97 was, and then C96, and then C95. It would take me a while to get to C100. If I had a formula that computed these directly, and it looks like we could come up with one, they're the powers of 2, CK turns out to be 2 raised to the k minus 1 power. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. Well, then we could compute C to the 100. It's 2 raised to the 99 power. And get there quickly. But I don't have this formula at the beginning of the example. I only had this formula. And this formula requires that I build my sequence up one term at a time. All right. So I have a question here. If this is my recursive formula, an minus 1 minus an minus 3, how many initial conditions would we need to compute the entire sequence? So C1 would be C0 minus C negative 3, and I don't have 0 or negative 3, so I would need to be given, I need to be given C1, because it's not C1, A1, because I don't have anything else to calculate with. A2 would be A1. Well, I have A1 now, because once I've been given that, I have A1. Minus A2 minus 3 would be negative 1. I don't have an A negative 1 to work out, so I would need to be given this one also. All right, so let's try A3. A3 is equal to A2. 3 minus 1 is 2, and I have an A2 now, minus A0, but I don't have an A0, and so I would need to be given an A3 also. But when I get to A4, finally we can do something. A4 is A3 minus A1, and I have A3 and A1. And so I can compute this one. And so the question is how many initial conditions would we need? We need 3 initial conditions. And it's usually based on the highest subscript that we see in the recursive formula here. The subscript here is n minus 3. We need 3 initial conditions here. Okay? All right. This notation, you've seen this notation also when you did things like Taylor polynomials, Maclaurin polynomials. If A sub n is a sequence and these bounds j and k are valid indexes for the sequence, with j being less than k, so that we're increasing the index as we go up, then this represents the sum of all of the terms of the sequence from j to k. This is the Greek letter sigma, and the S in the sigma stands for sum. Okay? So this is starting with the first term that's in the index is a sub j, and then we would add a sub j plus 1, and a sub j plus 2, and a sub j plus 3, all the way until we reach a sub k, and then we would stop there. For example, let's compute this term here. Starting at 0 and going to 3. This is a 0-based example. So this is going to be 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 to the 2 plus 1 over 2 cubed. This is 1 plus a half plus a fourth plus an eighth, which is, oh, well, let's try putting everything in terms of eighths so we have a common denominator. 8 over 8 plus 4 over 8 plus 2 over 8 plus 1 over 8 is 15 over 8. Okay? If instead of using a capital sigma for sum, this is a capital pi for product, then we are multiplying these things together instead of adding them. We don't see products as often as we see sums, but there is one sort of important case where we see products, and we'll talk about that in just a moment. So this is the same problem as before, but we're now doing the product. And so this is going to be 1 over 2 to the 0 times 1 over 2 to the first times 1 over 2 squared times 1 over 2 cubed. So this is 1 times a half times a fourth times an eighth is 1 over 64, I think, if we did this right. 2 times 4 is 8. 8 times 8 is 64. And so we get a different answer than what we got before. All right. Here's the example that I mentioned where the product notation is sort of important. This is something that we call factorial, and some of you have seen factorials before. You should have seen these at least in Calc 2. We define a factorial to be the product of all of the numbers I from 1 to n, if n is positive, and if n is 0, just as a special case, we just define this to be 1. Okay? So the example on the next slide, I want to go ahead and leave this formula up here, so I'm just going to do it on this slide. Asks us to compute 4 factorial. So that's the product from I equals 1 up to 4 of I, which is the same as writing 1 times 2 times 3 times 4. And that's 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24. And so that's the answer on the next slide. Compute 4 factorial. That's 1 times 2 times 3 times 4. And that's 24. All right. So if we want to compute 11 factorial over 9 factorial, that's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11. You do not want to work that out by hand. It turns out to be about 30 million or something. But 9 factorial is the product of all the numbers from 1 to 9. And we get some cancellation here. This is the nice thing about calculating with factorials, is that when we have to do ratios of them, we often get some very nice cancellation. And all we're left with is 10 times 11, which is 110. This would have been a lot worse if we had to compute the numerator and the denominator individually. There'd been a lot of multiplying, but because of the cancellation, we get just 2 terms that we have to multiply together, and that wasn't so bad. All right. So let's try using that to simplify this expression. I'm saying that n is greater than 2, so we don't have to deal with that special case in the denominator. If n was equal to 2, then we have this special case, and I don't want to worry about that special case right now. So n plus 1 factorial is 1 times 2 times 3 all the way up to, well, we'll stop at n plus 1, but just before that we got to n, and just before that we got to n minus 1, and just before that we got to n minus 2. I'm working backwards from n plus 1. This is 1 less, 1 less, 1 less. And n minus 2 factorial is just 1 minus 2 times 3 all the way up to n minus 2. And once again, all of these terms on top cancel with all of these terms on the bottom. And so what we're left with is n minus 1 times n plus 1. And to make the calculation a little simpler, I'm going to group these two together first, because I know something about a minus b times a plus b. I know the formula a minus b times a plus b is just a squared minus b squared. And so this is n squared minus 1 squared, times n. And so that's n cubed minus n. And so this expression simplifies pretty nicely without actually having to multiply out all those factorials. All right. We have a 3-day weekend, Friday, Saturday, Sunday. We don't meet Fridays anyway, but enjoy your weekend. I'll see you on Monday. Take care.